Let's continue. And so what you see here are the recorded strains, real life, and so on the upper plot you see the strains, and the lower plot the half of their difference and half of their pluses, because the half of their difference is proportional to the moment and half of the pluses proportional to the force. And then you can apply this model that we have used. Again, in this connection, I simply want to emphasize the best combination of any successful research when you successfully employ all the three ways of analysis: analytical, computer-aided. Certainly everything what you see here was checked and verified, and we found an excellent agreement between analytical predictions and finite element analyses. And here you can see the results. It's computed external tensile forces, bending moments for the measured strains on both sides of a printed circuit board. And the strain gauge reading in our tests were 556 times to the 10 to the minus 6, and so on. You'll see it, and using the obtained data, we found that the force was 1.5 kilogram per millimeter. That means per millimeter width in the distance perpendicular normal to the plane of the drawing. So 1.5 kilograms per millimeter, and the bending moment was kilogram millimeter by millimeter, so it looks like it's a force, but it's a bending moment per unit width. And the induced maximum shearing and peeling stresses were determined as were the numbers that you can see that. And we had, as I said, an excellent agreement between the predicted, of course, if we used the measured force and the measured bending moment as input data, we obtained excellent agreement with finite element prediction. If the action of the central force and the bending moment were considered separately, then the peak shearing stress and the peak peeling stress would be something completely different. So the interaction of the bending moment and the tensile force are such that we have to consider both. You remember at the beginning of my course, I've indicated that even if the analysis is linear, and here everything is linear, in many cases you cannot simply end up the results. The results are more complicated. So in other words, if you have a combined action of, in this case, bending moments and tensile forces, you cannot just do the evaluations separately for bending moments and separately for tensile forces, and then to sum up the results. You'll be misled. And this, even in a linear analysis, and in this case, that demonstrates that indeed the situations were different. In a situation when, in addition to bending, reactive in-plane membrane tensile forces occur, one can predict the two categories of stresses from the measured strains on both sides of the printed circuit board, and it's advisable that these two categories of stresses are evaluated based on both theoretical and experimental approaches. We have done that on a very limited base, and we feel that we had a very good agreement between the predicted tensile stresses. For instance, what actually I did for the printed circuit board, including, I considered also the fact that the mid portion of this printed circuit board was stiffened by the attached component. Even I also considered the fact that it was a compliant attachment, and based on the drop height, I predicted the tensile forces and bending moments. Then we did the rest of the analysis, and we found that was a very good agreement, surprisingly good agreement between the predicted and the measured data, and then we calculated the peeling stresses and the shearing interfacial stresses. And then it's beyond the scope of this course. We are applying these results to understand the long-term reliability performance of solder joints. Actually, the general approach is this way. The first approximation, we assume that everything is elastic. Non-linear elastic, but elastic. But because still, even if you have a ball grid arrays, it's only the peripheral joints that exhibit elastoplastic deformations, but their contribution to the total response is very small, and we can neglect that when we evaluate the total response of the system to shocks and vibrations, shocks in this case. Then we can subtract the elastic deformations of the board and of the printed and of the on the surface-mounted device, and determine the total elastic energy that is due to the attachment. Then in this attachment, we can apply one approach that I used in the past in application to photonic systems, and it's published in the European Journal of Applied Physics. And by doing that approach, I can subtract the energy which is elastic from the total elastic energy. And I can subtract the elastic energy in the mid portion of the assembly. So what was left of that, although it was not a very accurate prediction, but I hope it will be a reasonably acceptable prediction, we will evaluate the inelastic energy. We will compensate for that a little bit to use a conservative analysis if we consider that the entire energy is inelastic energy. In other words, the entire energy in the peripheral joints is inelastic energy, and based on that we can make a conservative prediction of their lifetime. Also in this case we'll probably use finite element analysis. So in this case the summary of this portion is this. We developed simple and physically meaningful predictive analytical models enable one to determine the role of various structural and materials factors that affect the stresses and strains in the bonding layer of a bimaterial assembly subjected to external tensile forces and bending moments applied to one of the assembly components, including those due to the dynamic response of a printed circuit board to an impact load applied to its support contour. The model can be helpful in the stress, strain, and reliability analyses of surface-mounted devices and printed circuit board assemblies in micro and optoelectronics and photonics. The calculated data based on the above analytical models are in good agreement with finite element calculations. The models can be successfully employed for the analysis of the dynamics of the ball grid array response on the board level and be used with confidence when analyzing the experimental data into developing, if necessary, new, more adequate experimental setups that lend themselves better to easy interpretation and long-term reliability predictions. That's our ultimate goal, and that's what we do now. Now, the next section in this course has to do with experimental evaluation of the effect of the initial position of a portable device on the possible damage of its IC, integrated circuit, as a result of a drop impact. I mentioned a little bit of that at the beginning of my course. And this project this effort is part of my project with Nokia, but this is Nokia in Manaus, Brazil. And when the Nokia Corporation in Finland decided, I believe about 5-7 years ago, to launch, actually to start selling their products in Brazil. The Brazilian government said, yes, you can do that, provided that your products will be manufactured in Brazil. And Nokia has established a huge factory in Manaus, Brazil, northern part of Brazil, 5 kilometers to the south of the equator, where they make Nokia phones. And I have a project with them. And this, what I'm reporting now on, is part of this project. And several people collaborated with me. The main collaborator was Dr. Luciana Arruda. And this is the test that we ran. So the initial position of the device was, as you see, that's alpha, and there were different alphas. And the degrees of these alpha are in the upper line from 0, which is a flat impact, to up to 75 degrees. And then we measured the number of hits. You remember when I described that to you, if it hits this way, then it can bounce back in several ways. For instance, it can go back with just that only touch, or it can touch the bottom, the concrete floor again. Let me explain a little bit of the physics. The first reaction is if this device hits the floor in the blunt way. In this case, you feel that it probably is the worst case, because you'll see a significant impact. The truth of the matter is just the other way around, because when we did the following experiments, if the portable device hit the floor the blunt way, it jumped much higher than when it hit the floor by the corner. The fact that it jumped much higher, that means that the part of the initial potential energy that was accumulated was transferred into the strain energy for the printed circuit board inside. We should calculate it as a difference between the initial potential energy and the residual potential energy after it jumped back. Because it jumped higher, that means that this difference was smaller compared to the situation when it didn't jump that high. And in the situation when it hit the floor this way, as a rule, it jumped much higher than in the situation when it hit the floor this way. Now, as I already described, when it hit the floor this way, we should distinguish between two conditions. One is it hit the floor this way, then it went back, and when it started rotating, it didn't hit the floor again, and then bounced at a certain height. And this height was higher than when it hit the floor, and then it starts rotating, it hits the floor again, and then it goes back again, and the height, the ultimate height, is not that high anymore. And it's true, we measured for this number of, and what you see here is simply the number of hits. If you see one hit, that means it didn't hit the floor twice. In some cases, they hit the floor twice, and in other cases, they hit the floor even 3 times. Then under other degrees of initial degrees, again, hit the floor just once. And what we did is we calculated, we measured also the bouncing height. And the worst situation is where the total bouncing height is the lowest for the same initial height and the same, everything the same. So we can see that the lowest was, let's say, around 6. It was when we had 2 hits or 3 hits. And this is an interesting observation. I calculated, I will not report it here, or maybe I put something here. No, I didn't put it here, that's fine. I calculated the rotational energy, so I did a certain analysis, which I didn't include into this course, but that sheds the light on the physics of this dynamic response. Again, it's a dynamic response different than what we discussed so far. It's not dynamic response of a structural element that it bends, that it stretches, that. It's like solid state mechanics. When we consider the initial potential energy, the rotational energy, all the type of energies, and have come up with interesting results, which in this course I will only report on the role of the angle of rotation, initial position of the device, not angle of rotation. And as we see here, this lowest bounce height, which is indication of the highest stresses in the printed circuit board inside the joints inside, happened at the degrees between, let's say, 15, 20, something like 15, 20 degrees. It's neither 0 nor 75%. It's something in between, which is an interesting and to a certain extent an obvious result. Test results with a strain cable attached. We also did the same thing with the strain cable attached. Of course, we should have in mind that if a strain cable attached and when we measured the strains in the printed circuit board, the free flight conditions changed, and it's not the same thing that was when in the previous view graph. But at the same time, it's also interesting whether indeed to what extent the number of hits are associated with the measured strains. And you see here that the results are such that with 1 hit, the first bounce height was higher, then it was lower. That was, again, with the different alphas, it was lower again. So this shows the role of that indeed the results were consistent. In other words, the conclusion that we made from the previous view graph where we measured what happens in the real flight, but we knew nothing about what happens strains on the level of the printed circuit board inside. From the quantitative point of view, it's pretty much the same. It's consistent with the results that we obtained here, although the absolute numbers are certainly different. The next is the elongated printed circuit board subject to the impact load applied to its ends, and this is, I consider for the sake of simplicity, a elongated board. And the point that I want to make here, I want to describe to you how it's different, the situation when we don't have a single degree of freedom system, but we have actually a elastic body. In this case, it's represented by an elongated printed circuit board because in this case, we deal with a, generally speaking, infinite number of the degrees of freedom. So what you see here for equation of motion, it's a close relative to what we saw, what we described at the very beginning of our course, but I just changed the positions of the leading terms. So the inertia forces here are not at the beginning of the equation, they're the second term, while the restoring forces is the first term. The restoring forces, elastic forces, have to do with the bending, and the loading per unit length can be interpreted as a product of the flexural rigidity of the board, and the flexural rigidity of the board, the formula is not written here, but it is in order to evaluate the flexural rigidity of the board, we have to, it's a formula, and the board is treated as an elongated plate. And the flexural rigidity of the board is the Young's modulus of the material times thickness of the board cube divided by 12 times 1 minus nu squared. Nu is Poisson's ratio. And that means that we treat a printed circuit board as a plate with uniformly distributed mass. Now, despite the fact that in effect the board is a composite structure, and it has fiber reinforcement inside and that and this, it's still acceptable to model it as a plate, thin plate with a uniformly distributed mass that makes the life of the analyst much simpler. And some evaluations that I did in order to consider the fact that you have the reinforcement inside, or the plastic material might exhibit viscoplasticity and that and this, I came to a conclusion that these complications are peanuts compared to the reaction response of the board to significant shocks, vibrations. You don't go to elevated temperatures where the material can exhibit high viscosity and that. So in my judgment, it's acceptable to do it this way and to treat a printed circuit board as a thin plate and to apply well-developed methods, more or less well-developed methods of the theory of thin plates that are well known in mechanics. So what you see here, W as a function of x and t is the displacement. And displacement, of course, is a function of the position of a particular point of the printed circuit board. And for this point, it's also a function of time. And the inertia forces, certainly, you have to take the second derivative of the displacement times to the mass, m, which is a mass per unit, in this case when it's elongated board, per unit width. And here, then, the major approach which is used in theory of dynamics of structures, the approach which is called the approach based on the principal coordinate method. This approach is known in the mathematical physics as Fourier method, when you have an equation in partial derivatives, which is the equation of motion, which the variable of interest, which is the deflection, depends on two variables, the position and time. You try to separate the role of these two variables and represent the deflection, as you see the second formula on the right-hand side. W is a function of x and t, and W is deflection of a certain parameter that we don't know in advance. We will find it. It's called the principal coordinate, that's a function that depends on time only, times a function, this is called coordinate function. We already mentioned that. in the beginning of this course, and that shows how the displacements are distributed for the given point of time along the printed circuit board. Here, take a look. It's clear from the physical point of view that when x displacement is the point which is located on the support, whatever happens to the board, the vertical displacements are 0. And indeed, when x is equal to a, the cosine of pi divided by 2, which is 90 degrees, is equal to 0. So this formula at least meets the boundary conditions. So we simply assume so far that this coordinate function cosine pi times x divided by 2a that was determined from the free vibration analysis for this linear system for the first mode of vibrations, that still holds for the situation when in the future it might be nonlinear displacements. But so far we know that in advance that it's the right coordinate function. Now the challenge now that is to determine the principal coordinate. If you know that principal coordinate, we'll know everything. So what we do, and this routine procedure, we'll not go through that, you'll take my word for that. We introduce the second formula into the equation of motion, and after that we'll see that this equation of motion will be satisfied if the first equation is satisfied, where g, which is flexural rigidity, times pi divided by 2a to the exponent of 4 times this principal coordinate plus m times f with 2 dots equal to 0. Then the next step is to divide everything by the mass. And in this case, and if you introduce the notation where omega for the board is pi squared divided by 4a and the square root g divided ma squared. In this case, we will see that the obtained equation where f2 dots plus omega squared times f equal to 0 is exactly what we already encountered with where we had a single degree of freedom. So what we did by using a certain approach from mathematical physics, we reduced the equation of motion at the top of the slide, which was written by for a system with multiple degrees of freedom, and we simply deliberately reduced the treatment to the first mode of vibrations. So for the first mode of vibrations, we received the formula, which is certainly not different, equation, which is not different from the equations that we dealt with from the very beginning for free vibrations of a system with single degrees of freedom. And in this case, as you see the omega, the frequency of free vibrations can be calculated exactly by the same formula that we use at the very beginning, which is square root of the spring constant of this spring divided by mass if we will introduce this notation. The spring constant is g times pi to the 4th divided by 16a squared. A is half of the length. And mass is mass times the a squared. An important thing that although by the form is exactly the same, but the mass in the treatment of at the very beginning of my course, the mass was the actual mass of the system. Here it's so-called based on what we did and how we did it correctly and everything. It's a generalized mass, and it's what I say in this note. The generalized mass is different of the actual mass of the system. And indeed, the actual mass of this board would be 2a so squared, right? If it's in both directions, times m. But here it's only m times a squared, so it's by a factor of 4 smaller than the generalized mass is by a factor of 4 smaller than the actual mass. And the explanation physical is very simple, because it's not the entire printed circuit board is subjected to the same acceleration and the same forces. The endpoints of the board do not move, and therefore different points of the board exhibit the external loading, inertial loading differently. No wonder that this generalized mass is different and is smaller than the actual mass of the board. And the spring constant, that's an interesting formula that was obtained for this case. Here we limited our analysis to the main principle, first mode of vibration. Now we'll make a break, and after the break we will discuss the role of higher modes of vibration, how we can consider them, how important they are, and in which cases we can afford to get away without considering their role. See you after the break.